Oh, welcome guys. So in this video, let's prove one cute results of the probability theory. We say that if the higher moment exists, then the lower moment also exists. Okay, so theorem is that R be the moment of random variable x is finite if this x r to the absolute is less than infinity. Then we want to show that for s less than r, s moment is also finite. Okay, so before we start, let's see a very easy example. Suppose that you know the second moment is finite, then you can easily prove that the first moment is finite. Okay, so this is like the easy corollary of this fact. The reason is that the e of absolute x is negative infinity to infinity x f dx. So f is a so-called PDF, probability distribution, and you can write f as a square root f times the square root of f because f is a non-negative function. And by a famous Cauchy-Schwarz, then you get x square root f square dx, take a square root and the square root of f square, and take a square root. And this is what? This is 1. Okay. So this is ex square root. So you get the e of x, the first moment is less than e of x squared. Okay, so this term is finite, so this is finite. Okay, let's prove it generally. So the proof we just use some error bound. So some error analysis. So let's assume that exr is finite. Okay, so we want to prove that exs is finite for s less than r. So the key point is that you can write exr as this one, and the return as two parts. The first part is that the restricting absolute of x in 1 or in negative 1 to 1, and the second term will be x absolute value x greater or equal to 1, and the f of x to r dx. And the important thing is this is finite, right? So these two terms must all be finite because they are all positive. Okay, so these terms should be finite. Okay, and when x greater or equal to 1, then x absolute of x r to the power r will less than x to s, right? Obviously, because s less than r. Okay, so ex to s can also be written in two terms. So the first term must be finite because this is a continuous function at the integral of the complex set. So this term finite. And this term must be also be finite, right? Because x to the power s is bounded by x to the power of r. So this term, the second term, will be bounded by this term. So less than infinity. So the proof are done. Okay. So there's a one sentence proof basically summarize this integral statement. Just prove that s to the power s is less than maximum x to the r and 1. Okay. The reason is that if x absolute value of x is less than 1, then definitely less than 1, right? If it's greater than 1, then it can be bounded by x to the power of r. So if you take the expectation value for both sides, then definitely you get results. Okay, so let's final remark is that the converse is not true. The converse means that if we only know lower moment exists, we cannot conclude that higher moment exists. Okay, so the easy example is that let's take a so-called Cauchy distribution. So Cauchy distribution is x2 over pi 1 over 1 plus x squared. So what, right? S greater than 0 and less than 0 is 0. Okay, so integral of f is 0, f is 1, right? You can check it because integral of 1 plus x squared dx will give you arctangent, so it's 1. Okay, so the zero moment is just 1, right? Oh, every probability distribution, 0 moment is always 1. And it's easy to check that first moment you get some x, right? So it becomes natural log 1 plus x squared. Put infinity, blows up. Okay, so that means that the 0 moment exists, but the first moment does not exist. Okay, so the converse is not true. Okay, that's a proof. Okay, very easy. I will see you guys in the next probability theory videos.